Imagine a world where numbers only go one way positive. You can have one apple, $5, 10 steps forward, but what about owing money? Or moving backward? Or temperatures below freezing? For much of human history, that's exactly how numbers were thought of. Positive quantities and zero maybe, but negatives? They seemed absurd. How can you have less than nothing? Yet today, negative numbers are indispensable. They're not just a convention, they're a profound extension of mathematics that unlocks deeper truths. In this video, we'll explore why negatives were invented, what problems they solve, and how they reveal the elegant structure of numbers themselves. Let's start with a bit of history. Ancient civilizations like the Babylonians and Chinese dealt with subtraction in equations, sometimes getting results less than zero. The Chinese, around 200 BCE, used red rods for positive and black for negative in calculations, practical bookkeeping for debts. In India, by the 7th century, Brahmagupta formalized rules. Positive plus positive is positive, negative times negative is positive. But in Europe, negatives were dismissed as fictitious until the Renaissance, when solving equations demanded them. The most intuitive way to see negatives is the number line. Positive numbers stretch to the right of zero, negatives mirror them to the left. Why this symmetry? Because addition and subtraction become translations. Adding 3 moves right, subtracting 3 or, adding -3 moves left. Subtraction is now just addition of the opposite, b equals a plus b. This unifies operations beautifully. Without negatives, subtraction is a separate, messier rule. In physics, velocity needs direction, plus 5 meters per second forward, -5 meters per second backward. Temperature scales like Celsius set 0, arbitrarily water freezes at 0 degrees Celsius, so below is naturally negative. More critically, polynomials demand all roots. The fundamental theorem of algebra says every polynomial has roots in the complexes, but even for reals, negatives are essential for consistency. Consider x plus 5 equals 3. Solving? X equals 3 minus 5 equals -2. If negatives don't exist, this simple equation has no solution. But the deepest reason? Equations like x squared equals 4 have solutions plus 2 and -2. The positive root is obvious, but without negative, we'd miss half the story. At its core, negatives complete the integers into an abelian group under addition. Every element needs an inverse. For 5, it's -5, because 5 plus -5 equals 0, the identity. Without inverses, you can't subtract freely. With them, the structure is symmetric, elegant, and closed. This pattern repeats. Rationals, reals, all need negatives for the same reason. And this idea of opposites extends further to imaginary numbers solving x squared equals -1, completing multiplication. Negatives aren't just useful, they're inevitable for a coherent number system. So why do negative numbers exist? Not because someone arbitrarily invented them, but because the world has opposites, equations demand solutions, and mathematics craves symmetry. They turn less than nothing into a powerful idea: direction, balance, completion. That's the quiet beauty of math. It extends our intuition just far enough to capture reality's depth. Thanks for watching. If you've ever wondered about another why in math, like why 0 or why I, let me know in the comments. See you next time.